Hello, the Qrise team and the IBM team. This is the submission of QExplore. I am Benjamin Atadana, and with me is Murat, Texas, students at Ankara University, Biomedical Engineering. And in this presentation, we'll be describing our task, the implementation, the results we had, and the references we consulted. Now, before we go ahead, let me just give a general overview of the protocol that we implemented. So we simply encoded an image using the amplitude encoding, then we teleported it, and then we decoded it basically. So let's say we start with a 3-channeled image, we converted it to a 1-channeled image, and the idea here is that if this is the RGB channel, then this pixel, and the last one are converted using modular arithmetic to just one integer over here using this code here. And so when we do that for all of the successive channels, we will have an n by n image. Now this is not entirely necessary for our protocol because we could have easily started with 1-channel black and white image and we could still move ahead. But this was to just enable us to encode this number of pixels with the same number of qubits, even if we're using just 1 channel. So whether 3-channel or 1 channel, we still use the same number of qubits. So moving ahead, we can say that we have 9 pixel values here, and then we normalize these values, and the sum of them equal 1. And the idea is that the value here should encode for the probability of a basis state occurring. Now these are 9 pixel values, and so the least number of qubits we will need should be 4 qubits to encode for 16 basis states as shown here. But since we just have 9 pixel values, we will just be using 9 basis states, and so the rest will not be used, and this will throw an error, and so we append this column vector with zeros, and so at the measurement all of these probabilities will be 0, and then these probabilities will be determined by these pixel values basically, right? And so this is the initialization of the circuit, and then we teleport it and measure. So from this measurement we can convert the probabilities back to amplitudes, and then we just do a back stepping. So let's say that we have 100 shots, and so the probability of this pixel occurring is 40 over 100, and we know that amplitudes, the square of the amplitudes is equal to the probability, so we could just use square root to get the amplitudes, and then we move back as we did to encode it, and then we undo what we did again, and when we do that we get the decoded result. Now this is the entire circuit that we have the initialization over here, and then this is the channel state, the entangled state, and half of these qubits are at the sending end and half over here at the receiving. So we could see the difference here. This is Bob receiving end, and this is Alice sending end, and this is Alice S for the state that you are encoding, and this is Alice channel for the channel state. So these are entangled, and this circuit implementation was taken from a paper which we referenced. And then again we have the teleportation protocol, and this is where the dynamic circuit's coming, and based on these measurements we apply either an X or a Z gate, then we measure, we decode the results, and then we get our original image. So this is the place that we implemented our dynamic circuits. Now the results that we had, so let's say that we start with this original image. We use modular arithmetic to encode it into a 1-channel image having these values, and then after we initialize the circuit, we teleport it and measure, we convert the probabilities back to amplitudes and backstepping, we have this decoded modular image. And then after we undo the modular encoding, we will have this reconstructed image. Now you can see that this and this are almost the same. This can be explained from the fact that the pixel intensities are relatively the same. So the maximum over here and the maximum over here are relatively the same. And so this pixel value over the maximum and this pixel value over the maximum would give relative intensity. So you would have this looking alike picture. But a problem arises when you want to undo the modular encoding. That when you convert this value back to the original three values that you started with, to the RGB values, when you convert this back to, so this converts back to 52, 211, 59, and this converts back to 52, 211, 60. And so we see that even though it's sort of the same for the first pixel value, we could say, when we look at the last, we have um, this value for 254, 152, and 225, and this is 13, 273, 97 for this value, and we could see gross differences. This is because even though they are quite the same, we have a difference in here. This is 1585.4 and this is 2731.3. And because it's modular arithmetic, you would have reminders somewhere. And so those reminders affect the pixel values that you would end up with. And that was a challenge that we had. But this is not necessary for the quantum encoding and measurement and decoding, because this is the quantum encoding and this is the decoding, and they are relatively the same, we could say. So this is a classical post-processing. And now for the challenges that we had, due to frequent updates, so in the Qiskit library, a code which was working a day ago, you wake up and it doesn't work again, and that was a headache at some point in time. And we've already explained the offset pixel intensities. And then unfortunately, we didn't really do a direct comparison between the static implementation and the dynamic circuits, the advantages they give, and then the noise characterization. We couldn't do that, and that's a challenge. Hopefully we'll work over it in the future. And then the choice of M and N for the encoding, we used modular arithmetic, and so we used some bases, and we chose 300 for M and N, which is not really secure, because using brute force, someone could come up with those values and then decode your image that you wanted to send. And that's also a challenge. And these are the references we used, and the entire code that we submitted is in here, and there are more details there as well. So we will encourage you to visit this repository and to have a look. Thank you very much for your attention.